start? It looks like you have seen the homeworks of today's lecture, so I try to be careful. So if you have any, please take a look at them if you have any questions before leaving. Ask me so I can help you. Okay. Let's start with the issues about the metric. So I just want to ask you one simple question. So how many of you have measured the distance and found an imaginary number? How many of you measured the distance, let's say, between the 2 points A and B and found an imaginary number? None, right? So you see who's using the weird metric. So I rest my case. Okay, let's proceed then. Okay, there is one thing I promised but didn't tell you and you didn't ask me. So I told you I'm going to tell you what TME nu is also called energy momentum tensor. And okay, let me tell you, let me remind you what TME nu is. The definition was this is how I define or how we call that in TME nu. So then the Hamiltonian will be given as T00 So if you actually look at our definition of the Hamiltonian and compare with this expression, you realize actually the 0,0 component of the T, the energy momentum tensor, is giving you the momentum density, Hamiltonian density. Also, if you look at the 0I components of the energy momentum tensor, you realize minus I Q, and we will come with this. We will encounter this expression again, and in the homework, you will have you will need to compute this and write this in terms of the integration creation operators. And that's why, since certain components of the energy momentum tensor are related to the Hamiltonian and the momentum, it's called an energy momentum tensor as well. Okay. So another thing I wanted to tell before I continue is, actually influenced by Altuğ's lectures, he talked about let's say electron muon scattering, right? So you have one electron incoming, exchanging a photon with a muon, right? So actually here you also see locality, right? Because at any given time, if I have two particles, let's say one of them is electron and the muon, if I take a snapshot, so it's an equal time process, and I just see them at different places. And I told you, locality tells you, that the operator should commute. And actually you see the interaction between electron and muon is still local, because interaction is induced by the exchange of the photon. So electron is interacting, or the muon interacting with the photon locally. Okay, it's not like they're not really interacting with each other, but they exchange photons. And this is also very a way to think about locality. That the interactions in QFT are always local. Okay. So, at the end of my first lectures, I had a list of physical constraints for the quantum field theories. And we said they have to be unitary, They should have locality, point current invariance, causality, and stability. Okay? And let me go through them again and tell you give some more insight. Okay, first of all, we said they have to be unitary. And we said Hamiltonian is Hermitian. So this actually in return implies that the action is real. So when we are writing down our Lagrangian density, you need to be careful that the action turns out to be real. Okay? So then locality. Okay. We said, they have to be defined at certain points. And if you want to write the Hamiltonian density or the Lagrangian density, we can actually Fourier expect them. And because they are going to hit at a single point. Or similarly, we can actually have the fields which we are going to use to build our Lagrangian density or the Hamiltonian density, and those have to also have a proper Fourier expansion. And generically, they will look like something like this. So this is, I'm just want to give you some generic descriptions. And eventually, in 10 minutes, you'll start seeing them realized. Okay, let me write down first expression. So here, you may wonder what this K sum is. So actually, the K sum is there in case the field has more quantum numbers, like spin. Okay, then we also need to sum over them. And here, so this is for other quantum numbers. And of course, if you have other quantum numbers, so creation and annullation operators may also carry a label with respect to these new quantum numbers. And then I call this Fourier coefficients U alpha pk, so they can carry some momentum label, they can carry quantum numbers, as well as they can carry a 4-vector character, because at the end of the day, this field will be transformed under Lorentz transformations. It can be a scalar, it can be a vector. So somehow in your Fourier expansion in terms of annullation creation operators, this should be reflected. And the way it's done is you just define your coefficients such that whatever transformation properties you want to require for A will be carried by the U's. Okay, so this is a generic field expansion. So then we say it's point current invariant. So okay, first of all, point current invariance includes the translations. Right? So can I write a Lagrangian density which is a function of x explicitly, like the form vector or position vector? No, because if I have an explicit dependence on x, then it's going to break the translation invariance. So the Lagrangian density cannot be a function of x. So it can be a function of the field alpha and derivatives with respect to alpha. And how many derivatives and other things will be a different question. Okay? And in addition to, as I said, the fields will transform under the representations of the Lorentz group. That's one thing. But we also have tensors which are invariant under Lorentz transformation, such as the metric or the epsilon. Okay? Sorry. Let me just assume myself to mean cosine. Okay? So these are also invariant tensors, like, under the pointer Lorentz transformation. So I can also, in addition to the fields, I can also contract my fields with these fields and construct Lagrangians. Okay, so now the fourth one was causality. So, okay. For that I said, okay, since, what was the condition I imposed? I said, the field A, X, T, that's another field, A beta, at Y, T, should commute. That was our condition for causality, right? So if we have a field at two different points at the same time, they have to commute because they are not at each other's like light cone. If I take this as a definition, okay, if I take this as a definition of my field, do you think this is satisfied with this definition? In general, no. So if you take if you take as here space-like separation, if you look at the commutation with this definition, you may see that this commutation relation is non-zero. So physically, so if I just draw space-time diagram in one dimension. So if let's say I'm sitting here at a point, right, and then the light rays by convention are drawn by vertical line, diagonal lines, normalized as c is equal to 145 degrees, right? So causality essentially means I can do something here, and this can only affect other events in its lifetime. Because this is required if this an event here at point A can affect at a point B, that will require a propagation of information faster than light. Special relativity tells you nothing moves faster than light. So that's why any causal structure, to ensure the causal structure, the interaction should be within the light bulb. If I'm looking at this equal time commutator, which means, so since the vertical axis is time, I mean at equal time it's going to be another point B. If you look at this light bulb of this one, okay, so B has this red light cone, and the event A is not in the light cone of B. So these two events are not talking to each other. So whatever I do here should not affect whatever I'm doing here, which is manifesting itself as a commutation relationship. So this is why equal time commutation relationships are set to equal to 0 to ensure that these events are not interacting because they're not in each other's light cone. Okay. For this reason, since this is not equal to 0, we have to include other fields. And if I call it B, again, I may have some quantum numbers, this integral, the same factors that we call another set of parameters which are defining the transformation properties of D in new integration equation operators. So what I can do is, what I can show, define a field as the sum of a alpha x and a phase b vector x. Here is the phase. So I can take the linear combination of that field with a similar decomposition, and then it can be shown that alpha xt commuting with of this. Okay. So this is actually a manifestation of particles and antiparticles. So quantum field theory is solving the problem of causality by like using the fact that you have antiparticles as well. And this is manifesting itself in this like second field. Okay. And I will tell more about this tomorrow when I introduce the Klein-Gordon propagator. Okay.
Should we do this as a homework and convince ourselves? You mean finding that the commutator is always zero?
Sure.
Yes. Let us take that as a homework.
I already given too many.
Oh.
Okay, this homework. Okay, so in this lecture I want to talk about Klein-Gordon or field as harmonic oscillator. Okay. Is everybody familiar with the creation annihilation operator approach for simple harmonic oscillator? Okay, now. So I was also going to review it anyways. So the Lagrangian density for Klein-Gordon is 1/2 squared. And if you then write down the equations of motion using the Euler Lagrange equation, you get the Klein-Gordon. Okay. So the idea is we start with this like classical field and try to quantize it. So of course, I mean, if you have a wave, this is like more as a wave equation. In the wave equation, you can just write it in terms of the modes. And what we are going to do, I mean, what we understand under quantization is we are going to take these coefficients and make them operators and impose some computation relationships. And usually, this procedure is referred as second quantization, which gives you the impression you are quantizing something for the second time. But you're not. You are quantizing only once, because you have like, the numbers and you just make them operators only once. The reason why it's called like, unfortunately, second quantization is in the quantum mechanics, in single particle interpretation, this is like, considered as a wave function. But once you make those like, coefficients operators, apparently people back in the day thought, okay, when we are writing down this quantum mechanics for a simple particle and interpret this phi as a wave function and like make it like operators and quantize it for the second time. But you're not. So in like so in the, as I said, in the one particle like approach, this is like a wave function, but in the quantum field theory approach, it's an operator. And already like Althus are talking about how the fields can create like particle states. So when you was talking about the electron and the photon, you get an electron and then get an electron and a photon, and there you have seen the necessity to define a focus space, because you start with one electron, but like in a time evolution you can produce like multiple particle states.
May I ask something?
Sure.
Why do we use the harmonic oscillators as harmonic oscillators? Is it because
Okay, I will
it
get
already has the annihilation and creation operators that involves it? Is it because of?
No, because like, if you take the Fourier transform, if you look at this like, in the momentum space, then that looks like a bunch of harmonic oscillators. I mean, well, we will come to this. Okay? This is just like an interpretation, because if you just look at it in momentum space, then you see it looks like, you know, a bunch of harmonic oscillator with like, you know, different frequencies. Okay. Okay, so now I want to give you a simple harmonic oscillator. Okay, so simple harmonic oscillator has a Hamiltonian p squared of 2m plus 1 over n omega squared x squared. Okay. So, of course, like in quantum mechanics, that a little more explicit, these are operators. Okay, and then you have the momentum operator. You have the space representation of the momentum operator. Then you can write this as a time-independent Schrödinger equation as h bar 2n So the task is to solve this Schrödinger equation. Fortunately, this equation has been solved by Hermite, and this is an eigenvalue equation. You need to find like, you know, the function psi and corresponding like, you know, e's to solve this equation, and they've been found by Hermite. That's why we call them Hermite polynomials. And since I'm too lazy to write it explicitly, I'm just going to make a proportionality, so you have a normalization to make your states properly normalized. Then you have like, you know, a Gaussian term, because there's a, you know, constant alpha which is related to omega and m and h bar. Then you have like polynomials, which is again like, you know, it's time constant, which is depending on the like, you know, parameters times x. And these are the like polynomials. And energy eigenstates are h bar omega. So if you, so the potential is like a parabola, and then you have energy eigenstates, 1/2 h bar, 3/2 h bar, and let me also do all like, you know, the couple these wave functions. So in the ground state, when n is equal to 1, maybe I should also say this here, n starts from 0. Sorry, when n is equal to 0, when you're in the ground state, you still have like, you know, energy, vacuum energy, which is going to be problematic for us because eventually you will have a bunch of infinitely many harmonic oscillators, each of which will have a 0-point energy. And if you sum like, you know, non-constant things infinitely many times, you get an infinity. So you have like, you know, let's say, I mean, for the ground state, you have the Gaussian, and you may have wave function like this, and so on. Okay. But this is like, you know, okay, brute force way to solve the harmonic oscillator. There is a much cleverer way to solve the harmonic oscillator in terms of creation and annihilation operators. So if we define A let me explicit here, and W H bar X plus and if I can also define a dagger, which is the same thing except as a minus sign, because x and p are the Hermitian operators. If I take the Hermitian conjugate of A, x and p are going to stay invariant, but I is going to pick up a sign. So I have the same thing except a minus sign. And it turns out that, you know, the commutation relationship between the x and p operators, which is h bar, will lead to the other way around with this definition, that A and A daggers do not commute. Their commutation is equal to 1. Okay? And then you can easily show that the Hamiltonian can be written as A dagger as H bar. Okay? So this is also easy because, I mean, take this, okay? Write that down, and you eventually see things cancel and you'll get the Hamiltonian. Okay? And once you know this commutation relationship between A and A dagger, and you have the Hamiltonian, you can easily compute H, computation of A, H, which is given as A, and I mean, I didn't give them as homeworks, but if you haven't seen this before, please go like, very carefully through all steps I'm skipping here. This is very important. Okay. So knowing this commutation relationship, we can actually construct the whole spectrum of this harmonic oscillator with the energies and the wave function. Okay. To see this, let me look at this. Okay, so I want to find the spectrum of the Hamiltonian, meaning I'm finding state, energy eigenstate of the Hamiltonian. For the moment, I don't know what the epsilons are. They are just arbitrary real numbers, right? They have to be real because Hamiltonian is a Hermitian operator, and Hermitian operators have real eigenvalues. So I have this, and let me take a state, A, epsilon. It is a new state. Let me call it epsilon prime. Okay? So if I have, so this is a question mark. I don't know what it is, but I can compute it. So this is A, epsilon. And then I can actually commute H with A using this commutation relationship here. And I get AH minus A. Acting on this. But now I know what H is acting on epsilon, which is epsilon and then the same epsilon. So this is going to be epsilon minus 1. Epsilon. Oh.
Prime.
And this is my epsilon. And I should get like an epsilon prime. H acting on epsilon prime is epsilon prime, so then I get epsilon prime. So what's the conclusion? The conclusion is if we start like with the eigenstate of the Hamiltonian and add with an integration operator A, it creates another state which is again the eigenvalue, eigenfunction or eigenstate of the Hamiltonian, but the energy is reduced by 1 unit. Of course, this is in H bar omega. I say okay. But you know that the Hamiltonian is like consists of p squared and x squared, so it has to be positive. It cannot have negative eigenvalues. So you can actually start with any arbitrary state, eigenstate, and then apply a number of times A, and you'll eventually come to the point when A destroys the lowest energy state. So there must exist a state. There must be a state which is going to be destroyed by A. If I active this H bar A on epsilon 0, still 0, nothing changes. But A dagger A from the Hamiltonian I know is H minus 1/2. Okay? And from this I conclude that I got the same conclusion. I started with I concluded because of the positivity of the Hamiltonian that there must be a state which is going to be annihilated by A. I add with that, that's 0. I add like A dagger. So if I add A dagger to 0, 0. Then I wrote it as like a Hamiltonian, and then it turns out like this state which is destroyed by the A is as an eigenstate of the Hamiltonian with 1/2 again in H bar omega. Okay? So and then I can conclude the other states are going to be right? Because every time I act with A dagger, the way A is lowering energy by 1 unit, A dagger is going to increase them. And then to get any state I can apply to epsilon A dagger n times, and I get the state after normalization. I can create a whole spectrum. And if you want to actually find the state in the momentum basis, in the position basis, it's also simple because I mean you need to look at this. Write this down. So actually, once you write this down, you can use this and get the first order differential equation. Or, yes, first order differential equation, and solve the differential equation. This is 0, and then you will see that you will get the Gaussian. So from this operator formulas, you can get everything much cheaper and cleaner. So this was like the harmonic oscillator in one dimension, and we can generalize it, right? I mean, we can, instead of xp, let's write like as qp, and call it I, and I'm going to start skipping like the h bars. Then I get into like consider a system of like many coordinates, and then qi, p, j, let's say. So you can think this as like if I have like three-dimensional harmonic oscillator in x, y, z directions. So the momentum in the x direction, the momentum of x direction doesn't compute with the x coordinate, but it computes with like y or z. Okay. And then these are 0. Right? The x computes with y, y computes with z, and the corresponding moment also computes. So, okay. So now this is the crucial point. So this discussion have been limited to discrete systems. So I had like one-dimensional system, I had multiple-dimensional system, but it was always discrete. But from the earlier discussion, we know we are not talking about only discrete spectrum, discrete like number of fields. We have continuous. Okay. So, and we define, remember, like we defined this two operators starting like pi. They were converted to conjugate. And I can look at them in the Schrödinger picture. What I mean in the Schrödinger picture, I only assume, I'm not allowing them to evolve in time. I'm letting my states evolve in time, but keeping my operators fixed. Okay? Then the commutation relationship, this commutation relationship will be written like this. So you see the similarity. So I'm just like instead of like as I mentioned before, in the equations of motion for the classical fields, I mean you have seen that the fields are like the coordinates. So I'm replacing the field with the coordinate, the momentum with the conjugate momentum, and since it's not discrete but continuous now and labeled by the position in space, I'm using delta Dirac rather than Kronecker delta. And similarly here. You see, like if this is like this is a Schrödinger picture. You don't have any time dependence, but you can convert it to the Heisenberg picture, where you are letting the operators evolve and leaving the states fixed, and then they are going to like be converted to the equal time commutation relationship. Okay, so now our task is similar, like for our task for Klein-Gordon is similar to harmonic oscillator. So we have a Helmholtz conjugate, we have like all equations of motion. So we want to like find the spectrum. So let's look at like remember that in the axioms or the constraint of the field theory, let's look at the field in Fourier in momentum space. So, okay. One note is in order. If we are looking at the real Klein-Gordon field, which means the fields are real, then we impose a condition that the complex conjugate of this like momentum Fourier modes need to be equal to minus p. So if you impose this condition, then your field is going to be real. But you can remove this condition if you allow to look at the complex Klein-Gordon. Okay. So then what I can do is I can write this down and plug this into the Klein-Gordon equation, and I will get this. Equal to 0. Which looks like similar to the which looks like the simple harmonic oscillator. When now we have different frequencies. So our frequencies now depend on the momenta as this one. I have actually like a simple harmonic oscillator corresponding to each Fourier mode. Okay. Okay. So because of the similarity of the Klein-Gordon equation in the Fourier space, the Fourier transform, you can actually write the fields in terms of creation and annihilation operators. Okay, so then our field will be written as now here A's are operators, not only numbers. Okay, if I impose that condition to the reality, I can just write them in a more compact form. But there are some terms I'm just keeping in place. X, and then you have similarly the conjugate momenta, and this is going to be different up to this minus sign. Remember, like here when I erased? No, okay, when I erase like A and A dagger were in definition of the minus sign, and actually if you write the A and A dagger, the X and P in terms of A and A dagger, you will also have a single structure where like one of them is going to be the linear combination, a positive linear combination of the antication creation operator, and the other one is going to be the negative. Okay?
Question.
Sure.
When we were discussing causality some minutes ago, the field in the Lagrangian were A and A alpha and W A alpha. Now you seem to have switched to phi's and pi's.
No, yes?
Yes, the relation between these two sets.
Oh, okay, so, no, there A wasn't the vector potential. That was like a generic, it's just a field. Okay, here, remember I said like, through A, okay. First, like, we wrote like, the A like this, in terms of annihilation operators. And then we said, okay, this is going to break the causality, and we need to add like an another field, the face factor.
Yes.
So this is the manifestation of this. We have creation and annihilation.
Well, I was trying to ask more about the del mu A alpha versus phi.
Sorry again?
In the Lagrangian density, you have A alpha, right?
Okay.
And del mu A alpha.
Yes.
Yes. Del mu A alpha versus phi, the conjugate moment.
Yes. Okay, because for the Klein-Gordon, we remember from the first lecture we saw this also pi dot.
Mm-hmm.
This is one component. So this is okay. Okay, remember like
emphasize that they are the same thing.
Yeah.
Yes.
Yeah, exactly.
I hope everybody got that.
Okay, sorry. Okay, remember like when we were saying, okay, let me write down the Lagrange density. It was like 1 over 2 by the square minus. So, okay, this was my Lagrange density, and here you see like, and I also reminded you this can be written as. So this is the derivative of the fields plus the field itself. And here, like our phi is like what I call like generic A, like at the beginning of the lecture. Then I can, okay. So since I know, like, I mean, I always like impose this like commutation relationship for the field, so I can convert them into commutation relationships for A's and B's, A's and like A daggers. And this looks like similar to anything you have one, right? If you are looking at this at different modes, P and P prime, that gives you 0. But if you are looking at the same mode, then they're just giving you some this Dirac delta. But as I said, previously we had this spectrum. Now we have like the continuous spectrum. That's how you end up with chronicle delta.
Can I ask something?
Sure.
Can you please repeat the part where we derive this form of phi? How did you phi of x? How did we find that from?
Okay, the locality tells you that the fields creating like your excitations should be defined locally. At their points, and if I just add this field, and as also to mention, you just like consider particles in field there as excitations of certain fields. If this field acts on the vacuum, it's going to create a particle at a certain point. Right? And then I can write this in the momentum space. So that is going to, since it's localized in the position space, it's like spread like in the momentum space.
So we solve for phi p of t, phi of p and t, the thing at the equation as that one. You solved it and put that in in that equation. Did you?
Yeah, so okay, so this is my Fourier transform, right?
Yes, you solved for phi of p.
No, I just plug this into the Klein-Gordon equation, and then it will like act on this. Okay, then it will bring down p's, which you see here. Because if you're careful, this is like the momentum, the space-time part. Because the Klein-Gordon equation, okay, you have this like four diverges. So this four diverges x on this like exponential, but this is only depending on the x, the spatial cost. It's going to bring down like p squared, which is p squared. But the time is going to like as a derivative because I'm putting the time dependence on this like Fourier modes, and that's why this time dependence is going to act on this and like create like this frequency. So okay. Then I can write down the Hamiltonian as momentum space as A So this is your homework, so as you see in the handout, to drive this. And what I mean by that, let me be a little more specific. So you know the Lagrange density, right, of the Klein-Gordon. So from this, you can write the Hamiltonian density in terms of y and pi, and you know the Fourier decompositions of this two. So the task is to find the Hamiltonian density, which I already wrote on the board, plug this decompositions and manipulate using this computation relations, whatever you need, to get the simple form. So that's the task. Okay? Okay, so, and something should bother you here. And that is you have this computation relationship. This is going to give you an infinite number. Right? Because as in this case, if you just think about this, let's think about this discrete case. You have an infinitely many harmonic oscillators. And you end up with A times A commuting with A dagger. They all give 1, and you have infinitely many ones. And you sum all over them. You get an infinite number. Should we worry about this? Should we worry about because it's going to support any computational measurement? Well, you shouldn't, because when we are measuring stuff, we are measuring the difference, not the absolute value. If we measure two things, this infinite constant, whatever it is, will appear twice. And if you take the difference, there's infinite constant will disappear, and you can only measure the difference. So this is there, but we don't need to worry about in this case. So this is also kind of expected, because the Hamiltonian, since we are talking about the field theory, we are looking at over space-time, and space is extensive. The quantities the Hamiltonian, we argue, since the Hamiltonian is getting contributions from each single point or from space-time, it's an extensive quantity, and you're looking at the Hamiltonian of an infinite. This is how this is extensive infinite part. So this part is going to be useful part. Okay? And similarly, you can check these computation relationships. Okay? Did I put them on the homework? No. But this should also be homework. Sorry, I forgot. You should also check that, because it's actually very simple. Because once you have this, you look at look at the computation with this, and then once you commute this A, actually this is the same exercise for the honest to God simple harmonic oscillator, because this operator A will commute this part, right? This is exactly the simple harmonic oscillator, and this is going to create some delta Dirac functions, and also those delta Dirac functions are going to eat up the integrals, giving you this omega with the operator itself. So it should be pretty straightforward. And of course, then, since this is the same relationship here, H commuting with AP is giving you minus A, essentially, with this omega P, you should have a state, which we are going to call vacuum. That's going to be destroyed by AP. As I said, because we said the Hamiltonian, we require the stability of the system, or that the H has to be bound to low. If the state doesn't exist, imagine we don't have a vacuum state, which is articulated by AP, and AP can act infinitely many times. So we will start with this state and lower it as many times, and infinitely many times down, and this is going to have infinite minus infinite energy. And this system is not going to be stable. So that's why we require the system to have a vacuum state. Otherwise, it's not stable. And the good thing is that the kind of convention, of course, if H is acting on the vacuum state, right? H is acting on the vacuum. So we will activate this piece. That piece is going to give you 0 because the annihilation operator is on the right. But you have this infinite piece, and you may think, okay, this should be infinite. But we are going to ignore that piece and assume this is 0. So our vacuum state will have 0 energy. Okay. So then, how do we create states? Easy. We have the creation operators, and we can act with them on the vacuum. Okay? So this is going to be our some P, Q, another state. Let me put like proportional this time because I'm going to ignore the normalization for the moment. So I can create. So the thing is, if I compare it to two states, okay, let's say okay, this is P, Q. Let me just take like, two particle state, okay, P, Q. This is going to be A, Q, on the vacuum, or I can consider PQ, which is A, Q. Okay. So the thing is, if A daggers commute belonging to different modes, then I will end up with the bosonic state. If they don't commute, if there is an anti-commute, I will end up with the fermionic state. And here in this case, I don't need to choose like a Q specifically different than P, and I can put many P's. So which means I can create like as many particles as possible in the state mode, which is also mimicking, we are talking about bosonic excitations rather than the fermionic excitations. And one useful thing, okay, I don't want to like give you too much homework. That's why I'm just like I'm just giving it your own pleasure. You can take the Hamiltonian, act on this state, and see that energy is going to be. That's going to first one thing you need to convince yourself is if you this state is an eigenstate of the Hamiltonian, and the eigenvalue is actually the sum of the energies of each mode. Okay? And similarly, you can also define the momentum operator. This was also, I also talked about this at the beginning of the lecture. Okay? So actually, you can also, you should also convince yourself that you can act with this operator to this state and get this state, which is still an eigenstate, and get this state with the momentum. Momentum, okay, let me be specific. Here I mean the operator, here I mean its eigenvalue, which is going to be P plus Q plus blah, blah, blah. And of course, one question is, as I said, I ignored the normalization, but of course we have to also normalize them. So you can say, okay, if I take like the two momentum states and look at the inner product between them, this is going to be P, Q. Okay? This is like more or less what you do in quantum mechanics. But if you have like two momentum eigenstates, if you look at the linear product, this gives you a product pair delta. Do you see any problem with this? Why we should not choose this? Or are you fine with that? Okay, one problem is this is not Lorentz related. So I can create it if I just have this prepare this space in this reference frame and boost it. The right hand side, the normalization is not going to be embedded under the boost. So we need, and how do we see this? Imagine we do a boost in the third direction. Okay. So the Lorentz transformations will P in that direction, the third direction, they are going to be boosted. So it's going to be gamma P3 plus P, then phi is going to be gamma P plus A dot P3. Okay? And I also want to remind you, Kronecker delta, Dirac delta of two functions is equal to and this is just a mathematical fact. So it turns out if you go carefully through this, like if you do this exercise for P prime to prime, and these are like the three vectors in the boosted frame. If you do this, you will see this is going to be, this will take a derivative. 3. I only have one derivative because this is a product of 3 delta directs, but I'm only boosting in one direction. The other two directions are invariant, so I don't need to involve this derivative. So I just need to involve once. If I go through this exercise, what I will see is this equal to E over E prime okay? You see actually in the boosted frame, delta Dirac is not anymore delta Dirac. So it's boosted, it's changed. But this exercise teaches something. It teaches you that E prime Q prime is equal to the product of delta Dirac energy is a Lorentz invariant. Okay, because I'm writing it in the unprime coordinate, I just boost it to the like prime coordinate, it's like E prime times E the delta Dirac with the prime momentum. So that's why we are going to normalize our single particle states using that energy. Sorry, our energy factor. So this is going to be vacuum and then P Q yes. Okay. And then of course since so far what did we do? Let's recap. So we had the Klein-Gordon equation. We wrote it in the Fourier space, okay, and we recognized the familiarity with the simple harmonic oscillator with different frequencies based on the mode, okay. So then we said, okay, let's apply, and we wrote the fields in terms of A and A daggers, and then impose some computation relation as we did, for the simple harmonic oscillator. Then we realized for the stability of the system, we have to have a vacuum state, which is going to be annihilated by every single AFP, and then constructed our spectrum by applying A daggers. Okay, then we show, or then you're supposed to show that this state, the one we are creating, are eigenfunctions of Hamiltonian, as well as with eigenvalues like this, with momenta like this, and given here. And we constructed a whole spectrum, and then we wanted to normalize the states. And we said if you are looking at the one particle state, one single particle state, so we have to normalize it with the spectrum of EP to ensure Lorentz invariance, which is is spoiled here. So this is a bad choice. Okay. Of course, the natural question is, okay, I have this phi of x, and I can act with this state to the vacuum. What am I getting? Right, so I constructed this whole machinery, and I just want to know what it is. So to see this, what we can do is this. We can look at this in the momentum space. can act with this and create a vacuum and get this matrix out of it. And what you will see is this is just like the wave function of a plane wave. Okay. So from this, we can think this as a single particle wave function. Okay. This is acting on the vacuum. This is P. This doesn't matter so much. We can take the value of the y, so we take the inertial conjugate of this. Okay? But this should remind you this one. This is my point. If you look at in the quantum, this is we have here, let's say, this is quantum mechanics. If you look at this, like the momentum eigenfunction functions in position space, they also get this. Right? This is like a particle, like propagating with a definite momentum in space. And this what phi does is more or less the same. It creates a state. This could be regarded as like single particle excitation which moves. Okay. But so far, everything we did was in the Schrödinger picture, which is a formulation in which I'm keeping the operators fixed in time and let the space evolve. And we can switch back to the Hamiltonian picture, sorry, Heisenberg picture. Where we actually like now have evolved the operators. In the Heisenberg picture, you have a nice equation of motion. For a given operator O, the time derivative of this operator is the commutator of the operator with the Hamiltonian. Okay? So which brings us to one of the questions of the homework set, probably the last one. Because now you can actually look at this. And let me tell you the answer. Look at this. The evolution of the time derivative of the field is like its conjugate momenta, which is what is the definition. But the more interesting thing is the time evolution of the conjugate momenta, which is of the Nicholas-Peltier by which is a little more complicated. And I can, combine them together. And what should I get if I combine them together? And the second derivative of y will be y. Right, because if I take the time derivative of both sides, now this is going to be the second time derivative of the field. This is going to be the first derivative of the conjugate momenta, and I can plot this the expression for the conjugate momenta, the time derivative of the conjugate momenta, from the other equations of motion. If I combine them, I get blank order. So again, if I switch back to with these definitions of my fields, phi and pi, if I switch to the Heisenberg picture, where I let operator evolve in time, and look at the equations of motion, I recover again the blank order equation. Sure.
What's the difference? When we write the psi x in bracket notation, this should be the same. And why do you write this one?
Which
one?
No, here we have this operator. Okay. So what we did is on the psi, if you look at the blank order equation, look at the psi, there's a wave function. It's a number. Here is an operator. If it acts on the vacuum, it creates like a state. Here, the reason I'm looking at this, I'm trying to understand what this operator creates. And that's why I'm looking in the momentum space. And then it looks like, I'm just trying to make a comparison. Like the way you have a single particle, you have a definite momentum, like a plane wave propagating in space-time. Here, if you are acting on the vacuum and look at the momentum space, it looks like also a plane wave. Like it also looks like a particle excitation. So that's why when Alto was lecturing today, he was talking about like the fields acting on the vacuum are creating a particle. So in quantum field theory, we are looking at the particles as excitations of certain field. Okay. So similarly, as I said, in the Hamiltonian picture, you have again same Pythagorean equation. But okay, since we have switched to Heisenberg pictures, then we should ask what happens to A dagger and A. Right, they were operators, they were independent of time, so they also need to evolve in time. So for that, time evolution of A and AP can be computed easily. Okay, so that brings me to another question. Do you know how to show the left-hand side is equal to the right-hand side? Okay.
It has a relation which combines containers.
Okay.
I don't know.
Okay. Like your house of can. Right? Because I mean, then there you have like the formula for general X. And then you can look at the Wikipedia, you get the expansion, and this is exactly this one. And then what you'll realize that since Hamiltonian is written in terms of A dagger, if you look at the commutation relationship, it's going to commute 1 and gives you, let's say, A prime. I mean, AP is going to commute with H is going to give you A, the first one. But if you commute that with the other commutators, 0. So this infinite sum will truncate to the first commutator. And when it's commuted, when it commutes, and then it's going to pick it from a delta graph, it's going to eat up the integral. And will give it C. And similarly, it's not hard to guess if you have a dagger here. And okay, this is a horrible mathematical. Of course, only like the sign changes. And now, what can we do? Remember, like we had this operator. It was like a Schrödinger operator. It didn't have a time dependence. Now it has a time dependence. The time dependence is in the like A and AP and AP dagger. So this is okay. So what did we do? So if you start, okay, in the previous expression, if you look at your notes, or if you are taking notes, and if you look at your expression for only side of x, you will see it was e to the I p dot over like 3 vectors. But now, since I'm getting this like exponential, I'm going to replace a p or a p dagger with AP times exponential, so I can absorb this exponential into this. Then I call like P0 EP. So now in this expression, the exponentials are enhanced from like the exponentials of like scalar product of 3 vectors to 4 vectors. And this is like the last question, the second question of the problems of today's this lectures, to show this integral with this funny prefactor in the denominator with something which is a Lorentz scalar. This is Lorentz invariant. And this is Lorentz invariant. And this is since this is like Px is a 4 vector multiplication. This is like Lorentz invariant. That's why if you integrate something which is Lorentz invariant with this measure, this is going to be Lorentz invariant. Okay. So I think I want to stop here, and tomorrow I will start from here and talk about about causality a little bit. Because the promise was if you have actually constructed a field with AP and AP dagger, then you are going to get rid of the problems with the causality that the commutators, equal time commutators are going to be zero. So I want to talk about it. And after that, I'm going to define called the time-ordered propagator and move on to the functional methods.
Before you all go away, I have a number of announcements. Your internet connection at the hotel is apparently fixed, improved, it should work much better tonight. The buses from the university will go back to the hotel at 5:45. So you